and welcome to this 8th and final edition for 2025 of the Great Designs in Steel Technical Webinars. My name is Brian Esterberg, and I'm the Senior Automotive Market Strategist at the American Iron and Steel Institute. Today's presentation is leveraging artificial intelligence for optimized vehicle structural design with advanced high-strength steels. Before we get started, I'll offer a few reminders and housekeeping. Please save the date for May 20th, 2026 for our annual Great Designs in Steel Symposium. Once again, that'll take place in Novi, Michigan. We intend to open registration next month in January. Our Great Designs in Steel call for speakers closes soon. If you've not already done so, please submit your abstracts to greatdesignsinsteel.com. Do that right away. We'll begin reviews of those abstracts received starting next week. And exhibits and sponsor opportunities are still available for Great Designs in Steel. Visit greatdesignsinsteel.com for information or contact me directly. And I'd also like to announce our next GDIS technical webinar. In January, we'll hear the effect of substrate composition on liquid metal embrittlement susceptibility in third-generation advanced high-strength steels, presented by Jake Colburn of the ASPPRC at the Colorado School of Mines. Jake will join us for this presentation on January 13th, and registration is now available at the autosteel.org website. So your microphones have been muted. Please use the Q&A feature in Zoom to submit your questions. We will not be using the chat or raised hand feature. Again, as in past webinars, please submit questions using Q&A. My colleague, Dr. Hisham Aizat, our Senior Technical Advisor, will join Sheng to address your questions following his presentation. And as always, a recording of today's presentation will be made available on demand and at the autosteel.org website following today's webinar. It is now my pleasure to welcome Dr. Sheng-Dong Liu, President and CEO at Generality. His presentation is titled Leveraging Artificial Intelligence for Optimized Vehicle Structural Design with Advanced High-Strength Steels. Sheng, I'll turn the controls over to you. Good morning and welcome.
Thanks, Brian, for your kind introduction. Good morning, everyone. Thanks to Katie, Brian, and Hassan for coordinating the webinar. Thanks to AHSS for providing this platform. And thanks for everyone for joining the webinar. I'm Sheng-Dong Liu, President of Generality LLC. Today, I will be sharing how artificial intelligence is reshaping the way we design steel vehicle structures with a focus on improving performance, cutting costs, and speeding up the development. This is my LinkedIn QR code. I'll be happy to connect with everyone in the audience. I think LinkedIn is a very good tool for professional connections. Recently, I found even someday I go to the other world, we can still talk on LinkedIn. Okay, this is my QR code. So if you want to, I'll be happy to connect with everyone sent the invitation to me. Here's what we're going to cover today. The first, I want to give a brief introduction to Hexagon design and engineering solutions. And then what is AI in structural design? Then I will show you some case studies in crash worthiness and safety, NVH, and manufacturing. At the end, I will give some key takeaways and summary of today's presentation. Before we get into today's main topics, I'd like to borrow 30 seconds of your time for an elevator pitch. Generality is a value-added partner for Hexagon's design and engineering solutions. MSC1 is a unified license system that gives engineers access to a full suite of CE tools. Say if you have a one of the license software licenses like AI, and then you will have access to all the different type of CE tools. So that's a lot of things about the 40 different type of FEA, CE, CFD software in the package. That's the software includes Natron, Adam, CE fatigue, and forming and welding simulation tools, and there's a 3D printing simulation tools, and recently they have added autonomous driving tools also. So that's a kind of very good learning platform for everyone also. Thanks for your patience and for listening to my brief sales pitch. Now, I like to talk about why do we need AI, or why do we want to introduce AI in vehicle structure designs? Well, traditionally, CE simulation in vehicle structure design is very time consuming. You need to hire PhD or at least master degrees to run or set up CE models. To run the CE, it takes a long CPU hours, and it's very hard to handle all the complex processes, and it's you may make an inaccurate decision because you don't have enough data, and the decision may be you may get a kind of low quality type of results. And the most important thing is you may not be able to utilize all the historical data. So in the manufacturing history, we have accumulated lots of data in the past. If we cannot utilize them, that's a kind of big waste. Not only the test data, the data from the manufacturing plants, and also all the CE data, simulation data. We have simulated a lot of vehicle structures. It's hard without AI. It's hard to dig out all those data and have a full utilization of the data. So that's why we want we want to use AI to help us. So this slides give you some simple idea what's the AI, what is AI. So we provide a lot of images as data, initial data, and we can categorize them, label them like cats or dogs. Then we supply to the AI system. We call that a training process. We train the AI system. The AI system based on their rules, and to tell this picture is a cat, this picture is a dog, and this cat, this dog. So they built a lot of rules to automatically tell which one is which. So then next time we want to we can supply new set of data to see if the AI system can give correct answers. So if the AI do a good job, then it's okay. If the AI is not doing tell if the dog is AHSS is a cat, then that means there's something wrong in the algorithm. Then we need to use this new set of data to retrain the model. So that's a kind of called the supervised learning, machine learning process. We retrain the model till it's give correct answers. And where the AI are using, being used. This shows some typically we're using AI for the classification if the cat or dog like this type of thing, and also for regression. If we have a lot of data, we want AI to have to find the trend for us. The other one is doing predictions like a CE process. If we have a new vehicle structure, we want to know what's the crash acceleration curves or impact force looks like at some conditions. So they give us we ask AI to give us a kind of prediction. And this shows how we are using AI in the CE process. At the very beginning, we may have some design ideas. We have a lot of design variables, so we may have this idea, different ideas in this kind of variable plan, and then we start to build the CAD create a CAD geometry, CAD data, then generate a FEA mesh, build a FEA model. Then we run the FEA solver like LSDyna or Nastran or Abacus, those type of software. Then the FEA software outputs the give the output results like force and time curve, maybe also the stress strain distributions, deflections, those type of outputs. So next time when we have a new set of ideas or new design data, in that case, once the model is trained, it will enter the data into the AI system. It will automatically real time give us all the type of responses. So that's what's how AI is working in CE. This where can AI be used in the design process? The first is the at the pre-design stage, we can use for parametric studies and trial and errors to find which part is important, which part is not important, those type of things. Then after the design is done, we can do the optimization to find the better, the most optimal solutions. Once the product is in operation, we can also do the reliability study and robustness evaluations. So this graph compares the costs. So without AI, anytime you say for a vehicle crash, anytime we have an additional iteration, the computation cost basically is linearly increases. So if you have a 10 if each run is 10 hours, maybe 10 runs, it will be 100 hours. There's nothing. It's a very simple mathematics. But with the AI, it will be very there's some initial cost at the beginning. We need to run some models to train AI. But once we have AI, the model is trained, and after that, the computation cost is very minimal. It's maybe each run only take just a couple of seconds. So cost-wise, in case we need to do a lot of iterations like optimization, parametric studies. This very, very cost effective. Then to run AI, we start with some initial designs, like it's called the design of the experiment. We select some conditions, design conditions. Then as the picture, the animation shown here, we start with some limited number of uh, initial training model. In case this red point, it's used for the validation purpose. So if we have we have some a set of data, maybe we want to take say 90% of the data for training the model, another 10% of data for validation to see if the model works well or not. So in case we found the errors, if the error is not satisfactory, we need to retrain the model. In that case, we can increase the design, the space of design experiments. So this is called an adaptive design experiment. It's a very convenient in the AI system. Anytime you find something wrong in the DOE, in your current DOE scheme, it's very easy to change it to different schemes or add points, reduce points. So it's very much better than classical design of experiment methods. In the classical one, manually, if you in the process of DOE, if you find something wrong, it's very hard to make a change a different type of DOE method. Then this one compares the difference between the CE process and the AI process. So basically, CE work on physics. So it's all it starts from the physical principles like partial differential equations. Then AI start from data, so it's a mathematical process. So they are totally different. The CE is a very solid, have a solid kind of physical background. So you get a very solution following the physics rules, and AI. It's just kind of use some kind of statistics method or it's interpolation methods, all mathematics. It's the result you got. It may reflect the physical the reality, but sometimes it may not make any sense, physical sense. So basically, it's just a kind of mathematics processing. This picture, this slide shows the kind of algorithm currently implemented in the Odyssey Hexagon AI software Odyssey. I'm sure there's some other AI software they may implement most of the method, but there's maybe some difference. And this one tells how the AI predicts the accuracy of AI can produce. So depend on different applications, you may select a different method. So that's I want to emphasize on this slide is this is the most important thing for especially for the CE engineers or future AI engineers. if you don't understand all these methodologies, then your results just like a CE system, garbage in, garbage out. So CE system, same thing. If you don't know the background of the CE, you collect wrong data, and the results give you wrong results, and even you have a correct data, and if you don't know how to run CE, you still get the wrong results. It's really same as AI. So depends on how good you are in AI, you will get different results. Even you have the same set of training data, depend on the training method, you get different type of data, different type of results. AI now has been integrated in with many CE tools from multi-body dynamics like items and materials manufacturing like stamping process, welding process. I will show you some case studies later, and integrate with the crash safety type of simulation like LS-DYNA and CFD, and also, of course, the Natron and thermal analysis type tools. I want to show you some actual real-world application examples. This shows a kind of prediction of crash parameters. The the red color in here shows the AI predicted results. The blue color shows the CE Allodyna maybe Allodyna results. So what we can see is the crash mode matches pretty close to each other. And this curve shows the comparison of force, the impact force compared with the between the CE results and AI results. So as we can see at the, especially at the very beginning, the not only the crash mode, and also even the curves at every peak point, they matches very close to each other. So that's shows how accurate is the AI. This shows a full vehicle crash comparison between AI and FEA. It's AI. The FEA use FEA. It takes 3 hours to run this model, and once the model is trained, it only takes a few seconds to get almost similar results. This kind of overlap between the AI predicted crash model and the FEA predicted model. So they overlap with each other pretty nicely. But the computation time is much less. This shows AI is used for the occupant protection. In this case, we need to run the two software like items and LS-DYNA in order to use item to determine the vehicle dynamics and also the occupant positions, and use DYNA to simulate the impact process. So in this case, well, we only conducted 9 simulations between items and LS-DYNA. And so if we run separate, if we run two simulations, it takes 19 hours for each run. And now once the model is trained, right now it's trained with 9 simulations. The blue point shown here, that's the training point. Once the model is trained, it takes only less than 1 second to predict the head acceleration curves. As you can see from these curve comparisons, the curves matches with each other very nicely, and the accuracy is over 98%, and the time is 19 hours compared to 1 second. That shows the power of AI. This for the PartsCAN design, then we selected 12 different type of section geometries. Then for each section geometries, there's thickness and materials and size. So that's all. That's a lot of combinations to get a full set of results. Without AI, we need to run 15,000 FEA simulation, but with the AI, we only need to run 1,500. So that's 10% of the simulation amount of simulation. And this one is a kind of comparison between the acceleration curves predicted by FEA and predicted by the AI. And as we can see here, the acceleration curves matches to each other very well. Now I'll show you some example for NVH applications. And this is a Honda Accord vehicle. We want to optimize the design to make the seventh natural mode to be over more than 40 hertz. So in this case, we made 10 DOE runs. So we select that's maybe a thickness and yield plan, yield strength plan, and we select 10 points and train the model. So after that, we use AI to predict, to optimize, to find the optimized solution. So in case of without AI, we just run regular CE. The whole process may take 72 hours, but with the AI, it takes only 1 minute to get the optimized solutions that give 40 hertz of the front lateral banding mode. This is another example for the AI applied to the NVH. And this is kind of a real design for the tracker frame for the rear end. It's the rail is separate into 3 segments, and also for each section we use 3 different type of materials. This is called tailor welded blanks. Depend on the location, we may not want that much thickness, or we may want to use a different type of materials. So then that's for this rail, it's maybe made of 3 by 3 9 different type of materials and thicknesses, and there's some other cross members gauges for optimization. So in this case, without AI, without AI use a traditional optimization method, it may take about 15 hours. And with the AI, it takes only about 1/3 of the time to get the optimized solutions. And it finally, as a final result, it helps reduce 20% of the weight from the vehicle. Now I want to show you some examples for manufacturing process. Um, this kind of application for the metal stamping process. The material is DP 600, and to train the AI model, we need to enter the blank geometry, blank position, and the tool design. What type of die we want to use? We did something like 40 different type of DOE points. Each one it's a kind of transient process. Each analysis has 10 forming stages, and it's once the model is trained, every time we have a new design, a new blank, either new blank geometry or new tool geometry, then we can predict new simulation results on the blank. This formed part. You can get either thickness distribution or stress strain distribution, and this typical for stamping process. You get a 4 mm diagram. What the strain distribution looks like. So it's very powerful. This shows the comparison of the animation between the AI predict animation results and the Elastina predict the animation results. And this one shows AI applications for the welding process, resistant spot welding, and it's the AI is integrated with the welding simulation software. It helps reduce the testing and optimize the welding parameters. So it can help improve the weld quality, reduce the testing costs and also the time. Now I want to give some wrap up and give some key takeaway points. AI is transform the structural design. So use AI, we can accelerate the design, reduce the cost, reduce not only the reduce the computation cost, and also maybe in the future maybe reduce the labor cost also. So once the model is trained, anybody can use AI in the company. So even you can put the AI in the factory floor. The technicians can quickly run AI for say for stamping process, welding process. So yeah, PhD still needed for training the model, but the running the model we may not the PhD may not be needed anymore. And it's definitely it will improve the efficiency. It speed up the whole process, and it can utilize all different type of data. So the historical, either test data or simulation data, everything can be fed into the AI system. And the very good thing is now AI can help optimize the whole design process across all different type of domains, from static analysis to dynamic analysis to material database and acoustic NVH fatigue. Um, all of them together, AI can run from the whole process. Um, so the AI for the future engineer. So AI is very important, especially for CE engineers. So if in the audience, if you are a CE engineer right now, I would like to say congratulations, you are one step ahead. And if you are not, maybe use at the same time you learn AI, and also you need some kind of CE background to understand, to interpret the results. So the AI doesn't always produce the results correctly. And what I want to say is act now, embrace AI-driven solutions to revolutionize your vehicle structural designs. Thank you very much for your attention. Again, here's my LinkedIn QR code. I'll be very happy to get connected with everyone. And finally, I wish everyone a safe, warm, and healthy holiday season. And now I would like to give the stage back to Brian and Hassan. Thank you very much.
Thank you very much, Dr. Liu. This is pretty interesting information. Um, Actually, it's a very deep space. So clearly, if anybody has any questions, please use the Q&A function to submit your questions. In the meantime, I do have a few quick questions, Dr. Liu, if you don't mind. Um, on the slide where you showed the different algorithms, um, is the intent here to like in the past, for example, when we were at the beginning of you know utilizing FEA analysis and things like that, is the intent here that we would have the users or the engineers and designers trained on using these algorithms and then set them loose on those, or how do you see the future for this?
Yes, that's a excellent question. That's a great question. I think um, there's there has to be somebody who's expert in all those algorithms. So in the model training process, you have to pick the parameters, the methodology in order to produce the correct result. So if in the validation results validation process, if you find the results is doesn't give a correct result, say if you give a picture, a cat picture, it says it's a dog, and then you need to understand why this happens, how to fix it. Otherwise, you may not have any clue how to correct the results. So there, it doesn't need everybody to understand just the training process. There has to be somebody understand all the methodologies. So that's the value of the AI expert or the future CE people. So we know CE, like even you run the CE models, you still need to understand all those the background theories, like the shell formulation, hourglass formulation, implicit codes, implicit code. You need to have some ideas. Otherwise, there's no way you can train the model. But once the model is trained, then the life is easy. Anybody can use the AI. Just keep feed the system the pictures. Keep feeding the dog picture.
Yeah.
That's an operation operators. Any operator can do it. So we can bring the AI system into the factory floor. Anybody there can touch the computer, enter new data, keep feeds the system with the new data. So that should be two levels, I guess.
Well, then I guess one question is basically, it seems like training the model is going to take a long time, and so the question here, or at least the comment I received is, can you give us an idea on how long or how much time is needed to train the model? And I guess this is kind of a loaded question because it depends on the complexity of what you're trying to train the model on. So any idea, for example, for the welding case that you showed, any idea how long it might take to train the model, or how fast you can do that?
Yeah, that's another excellent question. That's most of the concern maybe for AI application, and the number of training models. It really depends on as you said, depend on the complexity of the system, complexity of the problem.
Yeah.
If it's basically if it's a kind of almost linear, if the linear system doesn't matter how many parameters in the system, with two models were good enough. Everything is interpolated in the middle. So the most beautiful one. Any linear model, you only need two points. But if once the nonlinearity goes higher, you may need more and more data for training, like design DOE animation I show in my slides. So that once the model becomes more complex, you may need more data. So normally I was recommended for each parameter you may need 3 to 5 training points. So if you have one parameter, maybe you need 3 to 5. If you have say 10, maybe you need 30 to 50. That really depends. So like that vehicle crash between items and the LS-DYNA, that's a very complicated system, but the model was trained only by 9 data points. That's really depends.
Okay. I have an observation that I saw on slide 15. Maybe it's a little bit of an optical illusion for me, but looking at the crush can problem that you showed, now clearly the mode, the crush mode, is similar, very similar. And so from an overall perspective, it looks good. But what I observed is maybe the strain distribution in the crush can is not the same. Is there I mean, is that something that needs to be addressed, or what are we looking at here?
Yeah, and that's another great observation. Yes, the normally it's easier to predict to match the force curve or displacements. That's in the FEA or CE process. This is the first level. All the strain
Okay.
and stress are derived from displacement and force. So that's a second level. So the error accumulates when
Okay.
it's in the process. So strain stress is a little more. Definitely you will have see more error than force and displacement. So
Okay.
the
Okay.
crash mode basically is controlled by the displacement. Yeah,
Okay.
that's right.
Good. Well, so you know, in a as you know, in a vehicle design or a body structure design, there are a lot of uh, constraints, either packaging constraints or styling constraints, and the likes. Um, when you come to, like, for example, the crash simulation that you showed, and you showed like a different cross sections that you're going to use, or different cross sections that are possible. Uh, it's again, and again, this is kind of like a naive question for me, but how does the model handle that? How do you teach the model to number one, honor all the packaging and styling constraints, and at the same time play with section sizes, section shapes, thicknesses, and things like that? It seems like a very complex problem. So I, I don't know. Maybe I'm rambling a little bit, but can you just in general comment on how we envision that in the future?
Yeah, I think that you can enter the constraint conditions in the AI system. So the AI during the optimization process, it's you set up the optimization targets. At the same time, you can set up the constraints. So the AI, all the results you produce has to be within this frame, so within this constraints. So in that case, you can enter all the geometric parameters as the constraints. So it make sure it doesn't go out of the box.
Okay, so like an optimization problem, you have the ability to enter constraints and limits
Yeah.
on certain things so that the model doesn't go haywire. So are we at a point where essentially I'm going to use an initial analysis or the initial analysis uh, to to train the model and then let it rip? This way, all the other pursuing or the downstream analysis become very, very quick and simple? Or uh, am I reading this wrong?
Sorry, I didn't understand clearly the question.
No, I meant, like, for example, you're talking about training the model, all right? And we
Yeah.
want to train the model. How are we going to train it? With what? Is it historical data, or are we training it with data coming out of the initial analysis, and let it afterwards conduct its own analysis?
Yeah, can be from two different methods. Is if you accumulated a lot of historical, say historical test data or historical simulation data, it's if you see there's a value pretty close to whatever the type of job you are doing right now, you can utilize all those historical data. If you don't find any historical data, then you have to start to create your own training model to think about all different type of design ideas, then to run
Okay.
the CE models for
Okay. Okay.
training.
Yeah. So as a follow-up question, I have a question here from one of the participants. So, in a general sense, AI, can it help me select the material grade, whether it be any grade of steel or something like that? Can it help me if I give it some set of if I teach it? Okay, if I teach the model some information, can it help select the grade, go and grab the right grade to use?
Yeah, that's a good question. That's a really what's the AI is good at it. So
Okay.
yeah, once you enter all the possible solutions on all the different materials data into the system, you run the optimization process. It will help you to you give the target, give the constraints, then it will definitely it will help you to find the either the material grades or this even the thickness or whatever the material related. Yeah.
Very good. Very good. Well, it seems like this is we've just basically scratched the surface, and it looks like we're going to have you back several times as we move here into the future because this is a huge area that requires a lot of understanding. So I wish to thank you very much for this presentation. It's pretty informative. Remind all the participants that this will be posted on the website. And I'd like to thank you very much, Dr. Liu, for this presentation. And I'll turn it back to Brian. Thanks.
Thank you.
Dr. Liu, thank you so much for this presentation. The examples and case studies you've shared are very enlightening. Yeah, so thank you to everyone for joining us this morning. Dr. Liu, for your presentation. As Hisham said, we'll post the presentation and a copy of the recording in the days ahead at autosteel.org. Hisham, thank you again, as always, for helping to organize and facilitate the discussion. If your questions didn't get addressed, Dr. Liu has provided his contact information, and please reach out directly. And just a reminder as we part here, save the date for Great Designs in Steel, May 20th, 2026. We do plan to open registration next month in January. If you've not already submitted a speaker abstract but would like to, please send that in through greatdesignsinsteel.com. And again, registration is open today for our next GDIS technical webinar. We will welcome Jake Colburn of the ASPPRC at the Colorado School of Mines to present the effect of substrate composition on liquid metal embrittlement susceptibility in third-generation advanced high-strength steels. That registration is available at autosteel.org. Thank you again for joining us. Safe and happy holidays to all. We'll see you next year.
Happy holidays.